So the first thing that we are going to talk about is Thevenin's theorem. I believe I talked about this very briefly, not in a conceptual sense, but just kind of what it is at the before we left for our holiday break. So Thevenin's theorem states that any linear two-terminal network can be replaced at the terminals by an equivalent voltage source V Thevenin or VTH in series with an equivalent resistance RTH. Okay. We're going to talk about the rules for what VTH has to be and what RTH has to be in a moment. But I want to talk about this. This theorem is not nearly as long as the superposition theorem, and it's a bit more succinct. Effectively, what it states is that if we have a linear network that contains two terminals, we can replace it with an electrically equivalent practical voltage source. Because a practical voltage source, if you recall from our last lecture, is nothing more than a voltage source in series with a resistance. Okay. This practical voltage source will contain two components, a Thevenin equivalent voltage and a Thevenin equivalent resistance. So now let's talk about how we find the Thevenin equivalent voltage. The equivalent voltage VTH is the open circuit voltage. And I'm going to underline that because it's very important. Measured at the terminals of the live electrical network where in this case, a live electrical network simply means that all of our independent sources are left. The equivalent resistance RTH is the resistance seen between the terminals of the dead electrical network. Where a dead network is one in which all of our independent sources are turned off. Okay? So we are going to find the Thevenin equivalent circuit of the following system. So this is a circuit that we're going to be looking at. Here we have a 4-volt source. Here, a 9-ohm resistor. This is a 3-volt source. We'll put a 10 ohm resistor up top. 5 ohm resistor here. Another 10 ohm resistor here. A 1 ohm resistor here. And a last 10 ohm resistor down here. Okay, so this is our circuit of interest. I'm going to make a quick copy of this. Okay. So the first thing that I want to point out is that at present, this network is not a 2-terminal network because there are no terminals. Okay. So when we find the Thevenin equivalent circuit, we can find it with respect to a set of terminals, or we can find it with respect to a resistance. Okay. So in this case, we are going to find the Thevenin equivalent circuit seen by the 1 ohm resistor. Okay. So I'm going to write that down. And we're going to go through the steps that we need in order to determine the Thevenin equivalent resistance. All right. So the first thing that we're going to find is our Thevenin equivalent voltage. So I'm going to paste my circuit here. So when we are finding the Thevenin equivalent circuit with respect to a circuit element, like a resistor, we take our resistor of interest out of the circuit, okay? So if we're finding the Thevenin equivalent voltage with respect to the 1 ohm resistor, we remove the 1 ohm resistor because we don't want its behavior influencing the equivalent circuit. We're trying to see what the 1 ohm resistor sees. So I take that resistor out, and in doing so, I leave behind a set of terminals. These are the terminals that I'm going to use to find the Thevenin equivalent, okay? My Thevenin equivalent voltage is defined as the open circuit voltage across these terminals, okay? Now, I have not specified any particular polarity for this one. In your homeworks and things like that, I will always tell you positive polarity on top, positive polarity on the left, etc. Okay, so I'll be very explicit about it. In this case, we are going to find the Thevenin equivalent voltage with a positive polarity on top. So we have defined what we are trying to measure here. This is our open circuit voltage, or our Thevenin equivalent voltage, and we can use any circuit analysis technique we choose in order to solve for this quantity. So you guys tell me how you would like to solve for this particular quantity. Nodal analysis, mesh analysis, anything you think will stick, we'll explore. Mesh, all right. So, Gabriel, how many meshes do we have? I disagree. Requires it to be a closed thing, right? So we have this mesh, which I'm going to call IA. This mesh, which I'm going to call IB. And the bottom right-hand bit isn't a mesh because the current flowing through that would have to be 0 because of the open circuit on the right-hand side. Okay, so a bit of a trick question. So we have identified our meshes, labeled our mesh currents. There are no dependent sources, so we don't have any controlling relationships to write. There are no current sources, so we don't have any current relationships to write. we can get straight into writing our Kirchhoff's voltage law equations here, okay? So KVL at mesh A is going to look like -4 volts plus 9 ohms times IA minus IB plus 3 volts is equal to 0. Anybody have a particular problem with that? All right. If that one's correct, we can move along to our Kirchhoff's voltage law equation at mesh B. And starting at the bottom left-hand corner, we're going to have 9 ohms times IB minus IA plus, let's see, 10 ohms plus 5 ohms plus an additional 10 ohms times mesh current IB is equal to 0, where I'm effectively just putting those 3 resistors in series as a single equivalent resistance because they all appear as if they're in series from the perspective of our mesh current IB. And so now we have 2 equations, 2 unknowns. So let's take a moment to solve this system. So our coefficient for IA in our first equation is 9. Our coefficient for IB in our first equation is -9. And our constant term is going to be 4 minus 3 is 1. In our second equation, our coefficient for IA is -9. Our coefficient for IB is 9 plus 10 plus 5 plus 10. And our constant term is 0. And so when I solve this, I find that our mesh current IA is 34 over 225 amps. And our mesh current B is 1 over 25 amps. Did anyone get similar results? All right. So, Gabriel, not to pick on you, but you suggested this method. Now that we know these mesh currents, how can we use them to find the voltage VTH? So honestly, this is a little tricky, okay? I was expecting you guys to say, let's use mesh analysis, because once you learn mesh analysis, you try to use it for everything. And while it's absolutely applicable here, it probably isn't the best thing to use, okay? Now we're going to talk about how we can make mesh work in this case, but I would argue that since we were finding a voltage, nodal analysis probably would have been a better option here, okay? But let's make mesh work for what we have. So what I'm going to do is I'm going to define some voltages here. I'm going to call this guy Vx. I'm going to call this guy with this particular polarity Vy. And I'm going to write the KVL equation around this path. So this is at the bottom right, okay? And so I can see that VTH will be equal to Vx plus 3 volts plus Vy. Everybody okay with that? We've done similar things to this in-class assignments and all that kind of stuff. After we did mesh analysis trying to find a voltage, we had to write an additional KVL equation somewhere else to figure out what was going on. It's going to be in terms of our mesh currents. So 10 ohms times what we solve for as mesh current IB. I agree with that. What about VY? Why is it 0? You're absolutely correct, but why? Exactly right. The 10 ohm resistor on the bottom right-hand portion of the circuit, the voltage drop across that has to be 0 because Ohm's law tells us that V is equal to I times R. And since we know that the current flowing through that 10 ohm resistor is 0, because it's not part of a closed current carrying circuit or current carrying path, the voltage drop must be 0, okay? So 10 times IB would be 10 over 25 volts plus 3 volts. So that looks like 3.4 volts if my mental math is correct, because 10 over 25 is the same as 2/5, which is 0.4. Right. So this is our Thevenin voltage, right? So let's write that, sorry, more explicitly. VTH is equal to 3.4 volts. We could have solved this using nodal analysis. Off the top of my head, I can't really think of any other ways we could have done it. This is complicated enough to really justify using nodal or mesh. The key that I want to make here, or the key point that I want to make, is when solving for the Thevenin equivalent voltage, any circuit analysis technique that we have learned to this point is perfectly applicable. It's up to you guys to figure out which is the most efficient process. That being said, if we're trying to find a voltage, usually nodal analysis, if I'm going to have to write a system of equations, would be the one that I would use because it allows me to solve for voltages directly, okay? I don't have to take this additional step of writing another KVL equation and figuring things out, okay? Nothing wrong with it, but to me, it's not as efficient because I have to do two things instead of just one thing. Okay. All right, so any questions about this Thevenin equivalent voltage here? All we have done is just find the voltage drop across those open circuited set of terminals, because that's all the Thevenin voltage is. Now let's look at our Thevenin resistance. All right, so I'm going to paste my circuit again. We're still trying to find our Thevenin equivalent resistance with respect to our 1 ohm resistor. So we take our 1 ohm resistor out, leaving behind the set of terminals that we're looking into. So if we look into these terminals, we will find RTH, but we have to be looking at a dead electrical network, which means our voltage sources need to be turned off. Who can remember how we turn off a voltage source? Short circuit. So our 4-volt source gets replaced by a short circuit. Our 3-volt source gets replaced by a short circuit. And now we have a network made entirely of resistors. And so if applicable, we can just use resistor combination techniques. Kevin, how may I help you? Independent sources only. So we're not dealing with dependent sources today. That's going to be what we do Monday after the exam. But for a dead electrical network, only independent sources are turned off. So only the circle sources. Voltage and current. Yes, absolutely. If we had a current source, how would we turn it off? Open circuit, right? So turn off voltage sources with short circuits. We turn off current sources with open circuits. Okay. So because I'm just trying to find an equivalent resistance, I'm going to use simple resistance combination techniques. So I'm going to identify my nodes. That my 9 ohm resistor is shorted out. So that's something useful. So I'm going to call this node A, this node B. Let's call this C, and let's call this D. So I'm finding the resistance between A and B. And there is no direct path between A and B. So now let's look for our shortest path. So our shortest path would be from A to D to B. So I'm going to put D here in the middle. From A to D is the 10 ohm resistor that's in the middle. And then from D to B is the 10 ohm resistor that's on the bottom right. Okay. Now I could also go from A to C to D. So I'm going to put C here. To go from A to C is through the 5 ohm resistor. And to go from C to D is through the 10 ohm resistor on the top right. Again, the 9 ohm resistor should not contribute because it is shorted out. It's connected to the same node on both sides. And so from this, I can see that my Thevenin equivalent resistance is 10 ohms in parallel with 15 ohms. And that combination is in series with 10 ohms. Well, 10 in parallel with 15 is 150 over 25, which is just 6. 6 plus 10 is 16. And so the Thevenin equivalent resistance seen by the 1 ohm resistor is simply 16 ohms. Anybody have any questions, comments, or concerns regarding this resistor combination? All right, so let's tie things together. So according to the work we've just done, our original circuit and this circuit are electrically equivalent. Where this is VTH, this is RTH, and this is our 1 ohm resistor that we were finding the electrically equivalent circuit with respect to. From the perspective of the 1 ohm resistor, these are identical. Now we could find the power that's transferred to the 1 ohm resistor rather easily, all of that kind of good stuff, okay? So Thevenin equivalent circuit source representation connected to a particular load resistor, much like what we were doing prior to the break, okay? Except that we don't have to be able to do source transformation in order to get from a larger circuit into a practical voltage source connected to our load resistor. We can use any circuit analysis technique we're interested in, which is why I was telling you guys before the break that I think source combination is kind of a waste of time. Because Thevenin equivalent circuits are a more powerful way to get the same result. And as we're going to see in a moment with Norton equivalent circuits, that's how we go from any large circuit into a practical current source representation. Okay. And then we could say that the Thevenin equivalent circuit must be electrically equivalent to the Norton equivalent circuit and get our relationship there. All right, so this is what our Thevenin equivalent circuit looks like with respect to the 1 ohm resistor. Would it be different if we took it with respect to the 5 ohm resistor? Yes, very much so. Okay. So what we have developed here is only valid from the perspective of the 1 ohm resistor. If we take it with any other element, we would get different numbers. All right, so I want to be very clear about that. Okay, so now let's talk about Norton's theorem. So Norton's theorem states that any linear two-terminal network can be replaced at the terminals by an equivalent current source I Norton in parallel with an equivalent resistance, bless you, R Norton. So effectively, we can take any linear two-terminal network and convert it into a practical current source. Okay. The equivalent current source I Norton is the short circuit current that is important measured through the shorted terminals of the live network. And the equivalent resistance, R Norton, is the resistance seen between the terminals of the dead network. So one thing that I want to point out here is that the definition for the Thevenin equivalent resistance and the Norton equivalent resistance are literally identical. They represent the exact same thing, so you will never see me write R Norton again. I will say everything is a Thevenin equivalent resistance. Okay, they're the same thing. So let's take that same circuit and now let's find the Norton equivalent circuit with respect to the 1 ohm resistor. So the only thing that we're going to do here is we're just going to find I Norton. Because finding R Norton is pointless because we've already found R7, right? Since R Norton and R7 are literally the same thing, why bother finding it twice? So the Norton equivalent current is defined as the current that is flowing through a shorted set of terminals, okay? So since we're finding this equivalent circuit with respect to the 1 ohm resistor, we take our 1 ohm resistor out. And now we short circuit those terminals. And our Norton current is simply the current that's flowing through that short circuit that's replacing the 1 ohm resistor that we're interested in. Okay. Once again, in our problem statement, I did not particularly specify the direction for the Norton current. We are going to do it in the direction down. In your homeworks and all that kind of good stuff, I will make sure to specify the direction of your Norton current, just like I specify the polarity of your Thevenin voltage, so that there is no confusion or ambiguity. The reason why this is important is because in active circuits or circuits that contain dependent sources, it is possible to have a Thevenin equivalent voltage and a Norton equivalent current of opposite polarities effectively, so that you would wind up looking at a negative resistance, okay? Now, we haven't dealt with negative resistances in this class at all. They're actually all around us. The ballast for every one of these fluorescent lights contains a negative resistance. All negative resistance really means is that a positive voltage produces a negative current. That's it. Nothing particularly fancy or anything like that. As the voltage increases, the current increases and becomes negative. Still the same constant of proportionality. It's just our directions are backwards. Nothing wrong with it, but it tends to mess with people's heads a little bit. So I'm not going to try to give you anything that you'll see that with, but it is a possibility whenever dependent sources are in our circuits, okay? Without dependent sources, we should see that the resistance is always going to be positive. If we have a dependent source, it is possible to get a negative resistance. Nothing wrong with it. It is possible. All right. So how are we going to find this current I Norton? However we feel like. Mesh analysis is the obvious choice here. We can do that. We could also do nodal analysis if we wanted to, but let's just keep things easy and do mesh. So in this case, we have 3 meshes. IB and IC. So we have identified our meshes. We've labeled our mesh currents. Once again, there are no dependent sources, so we don't have any controlling variable equations to write. There are no current sources, so we have no current relationships to write. We can move straight ahead into our KVL equations. So KVL at mesh A is going to be pretty much the exact same thing we had when we did mesh on our Thevenin equivalent voltage. So we are going to have -4 volts plus 9 ohms times IA minus IB plus 3 volts is equal to 0. KVL at mesh B, we are going to have 9 ohms times IB, IB minus IA. Then we're going to have 10 ohms plus 5 ohms times IB. And then we'll have 10 ohms times IB minus IC. Set all that to equal to 0. And then lastly, we have KVL at mesh C, which is going to look like -3 volts plus 10 ohms times IC minus IB plus 10 ohms times IC is equal to 0. And we will solve this system. So this is the 3 equation, 3 unknown system, and it looks like I hit the wrong button on my calculator. There we go. So our coefficient for IA in our first equation is once again 9. Our coefficient for IB in our first equation is -9. And our coefficient for IC is 0, and our constant term is +1. For our second equation, our coefficient for IA is -9. Our coefficient for IB is 9 plus 10 plus 5 plus 10. Our coefficient for IC is -10. And our constant term is 0. In our third equation, we have no coefficient for IA. -10 is our coefficient for IB, and 10 plus 10 is our coefficient for IC. Our constant term is 3. Solving this system, I get IA is 17/72 amps. IB is 1/8 of an amp. And IC is 17/80ths of an amp. Did anybody else get similar results? Bless you. Camille, were you nodding your head that you got the same thing? Great, I'm going to move on. If one person gets the same as me, then let's keep it rolling. All right, so jumping ahead, once again, we don't need to find the Thevenin equivalent, or excuse me, the Norton equivalent resistance because we found the Thevenin equivalent resistance. We can say that the Norton equivalent circuit actually, let me go back here really quickly. So we found these 3 mesh currents, but we did not relate any of these mesh currents to I Norton. How do we do that? Well, yeah, IC is equal to I Norton. All right, thank you, John. So from that, our large circuit on the left is electrically equivalent to this. Our Norton current in parallel with our Norton equivalent resistance in parallel with the resistor that we were interested in. And then from here, we can infer that the Norton equivalent circuit and the Thevenin equivalent circuit must be electrically equivalent to each other, since they are both equivalent to our larger circuit. So in general, we know that VTH in series with RTH is electrically equivalent to I Norton in parallel with RTH, where our Thevenin voltage VTH is simply I Norton times RTH, or our Norton current is simply VTH divided by RTH, or our Thevenin resistance is VTH divided by I Norton. Just Ohm's law, or the exact same relationship that we developed when we did source transformation. Okay, so if we have a Thevenin equivalent circuit, we can convert it into a Norton equivalent circuit, and vice versa, just using the same rules that we learned for source transformations here. One thing that I really like about Thevenin and Norton equivalent circuits is that if you know two of the quantities, you can find the third, but if you know how to calculate the third, you can effectively check your work, right? Because if you know two, you can find the third, but if you can find all three, you know if the ratios are correct, whether you did things right. So there is an inherent way to check your work using this methodology. Okay. So the last thing that I want to do is work one more problem. Our goal here is to find the Thevenin and Norton equivalent circuits for the following circuit. So we have a 3-volt source, two kilo ohm resistor, seven milliamp source, five kilo ohm resistor, 1 kilo ohm resistor. We are going to find the Thevenin equivalent circuit with respect to our open circuited terminals. So whenever we find it with respect to terminals, we don't need to take anything out. Whenever we find it with respect to a particular element, we take that element out. Just want to be clear there. Okay, so this is our circuit of interest, and we want Thevenin voltage plus on top, Norton current, direction down, and our Thevenin resistance. So those are our three quantities of interest. And we're going to find these three things and then prove that we can switch back and forth. Okay. So let's find, what do you guys want to find first? The voltage, okay? So since this circuit already has an open circuit set of terminals, we're finding the Thevenin equivalent with respect to those open circuit terminals. The only modification that we need to make is to put our Thevenin voltage in our circuit. I told you specifically that we were finding it with a positive polarity terminal on top. Okay. So before we decide on how to solve this circuit for its Thevenin equivalent voltage, I want to make an observation. This is an observation that I make a lot when dealing with Thevenin equivalent circuits. Okay. What is the current flowing through the 1 kilo ohm resistor on the top right? It's 0, which means the voltage drop across the 1 kilo ohm resistor is also 0 from Ohm's law. So that means that this voltage drop across the 5 kilo ohm resistor is also another way to find VTH. Because Kirchhoff's voltage law around that right-hand path would tell us negative VTH plus VTH is equal to 0, right? So understanding that VTH can be expressed as the voltage drop across the 5 kilo ohm resistor, how would we choose to solve this? So the suggestion here is that the 7 milliamp current source multiplied by the 5 kilo ohm resistor is going to give me VTH. The problem with that is that it is not taking into account that some portion of the 7 milliamps of current might split off and flow to the left through that voltage source and that 2 kilo ohm resistor. So we could do nodal, but I would argue that nodal is slightly overkill, okay? Meshes is also overkill. I can solve this in one equation. Kirchhoff's current law. KCL at this top node, right? So if I apply KCL right here, I am going to be adding this current plus this current plus this current together, where I know I don't need to bother adding the current flowing to the right because it's 0, okay? So KCL at green node, I'm going to have VTH minus 3 volts over 2 kilo ohms plus 7 milliamps plus VTH over 5 kilo ohms is equal to 0. One equation, one unknown. This is effectively the exact same thing that you would get by doing nodal analysis, except that we don't have to bother writing our voltage relationship equation and doing a substitution. It's already buried inside this equation. I would then need to throw this into my numerical solver to solve for it. So let's do that really quickly, which means I have to remember how to use the solve function on this Casio calculator. Let's see. So I want to go to this function, and then I'm going to have, let's see. X minus 3 over 2000 plus 0.007 plus X over 5000 equal to 0. Solve. I got negative 7.857 volts. Yes, Bree. The VTH minus 3 over 2 kilo ohms. So this might make things slightly easier. Treat that as if it's ground. So we have the nodal voltage effectively where the current is starting from, which is VTH, minus the nodal voltage that it's flowing to, which is 3 volts with respect to ground. So I have VTH minus 3 volts divided by 2 kilo ohms is the current flowing to the left. Current flowing down on the left-hand side is 7 milliamps, so that's added. Current flowing down through the 5 kilo ohm resistor is VTH minus 0 over 5 kilo ohms. Yes, ma'am. Okay. So this is for the Casio FX991EX because I bought a new one over the Christmas break. So I entered this in as X minus 3, where X is just my variable that I'm solving for, divided by 2000, plus 0.007, which is 7 milliamps, plus X over 5000. Then I hit alpha and then the calculate button because that gives me my equals and then set it equal to 0. And then I pressed shift and solve. or shift and the calculate button to solve it. And then I give it something to start from. It's very similar on the Casio 115s. For those of you who have a TI, I don't have mine on me. Can I look at yours real quick? Okay. So for those of you that have the TI 36Xs, if you hit shift and then the sign button, it brings you to numerical solve. And then you literally just type in your equation, set it equal to 0, and press enter to solve the equation. So I prefer doing one equation, one unknown calculations on this type of calculator because it's easier to remember how to do it. Once again, I'm a weirdo that has a favorite calculator for different operations. I will happily come by and explain how to do it to you, but I don't want to eat up too much time here. So this is the value that I got, and we found that the Thevenin equivalent voltage is a negative quantity here. Is that going to be a problem? Probably not. We should expect that since we only have independent sources and resistors, our Norton current with the direction down is going to wind up being negative as well. So let's figure that out. So to find my Norton equivalent current, I simply short circuit my terminals. Find the current flowing down here. And we could do anything that we wanted to here, but I would argue that mesh analysis is probably the easiest thing to do. So here's IA. Here's IB. Here's IC. So our mesh currents have been identified and labeled. We don't have a dependent source, but we do have a current source. So we're going to need a current relationship equation. So that is going to be 7 milliamps is equal to IA minus IB. We also have a super mesh because we have an interior current source. So that super mesh is between meshes A and B. So KVL at super mesh AB is going to be -3 volts plus 2 kilo ohms IA plus 5 kilo ohms IB minus IC. Then we're going to have KVL at mesh C. So that's going to look like 5 kilo ohms times IC minus IB plus 1 kilo ohm is equal to 0. And we will now solve this system. So this is a 3 equation, 3 unknown system. Our coefficient for IA in our first equation is 1. Our coefficient for IB is -1. Our coefficient for IC is 0. And our constant term is 0.007. In our second equation, our coefficient for IA is 2000. Our coefficient for IB is 5000. Our coefficient for IC is -5000. And our constant term is +3. In our third equation, this should have an IC right here. Our coefficient for IA is 0. Our coefficient for IB is -5000. Our coefficient for IC is 5000 plus 1000. And our constant term is 0. Solving this system, I get 53 over 17,000 amps for IA, -33 over 8,500 amps for IB, and -11 over 3,400 amps for IC, where IC is equal to I Norton. So using our results here, our Thevenin equivalent resistance should be negative 7.857 volts divided by negative 11 over 3,400 amps. So let's see, negative 7.857 over negative 11 over 3,400. 2.428 and some change kilo ohms. And let's just verify that by finding the Thevenin equivalent resistance directly. So my Thevenin equivalent resistance is just the resistance seen looking in here at a dead network. So that means my 7 milliamp source is replaced by a open circuit. My 3 volt source is replaced by a short circuit. And so this looks like 1 kilo ohm in series with 2 in parallel with 5. So that is going to be 1 plus, let's see, so 2 times 5 is 10, 2 plus 5 is 7, 17 over 7, or 2.428 kilo. The exact same result. We got either way. All right. So unless anybody has any questions, I believe that is enough out of me. I will happily come around and show you how to use your calculator and all that kind of jazz if you feel that you need it. I will also answer any questions you may have regarding the content.